So welcome everybody. I'm the head of the School of Physics, and it's a genuine pleasure for me to introduce one of my favourite colleagues, Professor Joe Wolfe. And not only has Joe prepared a talk tonight, he's even prepared some notes for me to introduce him. because he knows it's safer to actually write these things down and let me ad-lib. Now, I met Joe 22 years ago. I came here in 1990, I think it was, to visit the school. I hadn't realised that then he was a specialist in cellular statistical mechanics, which I'm unable to enlighten you further, but he probably will answer questions if you want to know that. He made his career switch into 21st century physics by moving into acoustics. And he put up a lab then, and it took him a couple of years, I think, to switch fields, but he was already an accomplished musician at that stage, and he specialised in the physics of the voice, of the ear, and musical instruments, of which you can see a good selection here tonight. And it'll be interesting to see what sort of music the climbing rope can produce. Joe and his colleagues have made a number of educational web projects. The one that's really famous is PhysClips. I urge you to look at that. Very popular with high school students and teachers. In his spare time, Joe is a composer himself of orchestral and chamber music, and one of his compositions has recently had its first African concert, and that means that this piece has been performed on all continents except Antarctica, which is fantastic. So I'll hand over to Joe. Thank you very much for doing this, Joe.
So as Richard said, there's a couple of online footnotes. The lab's website on the top there not only does the sort of self-promotion that lab websites often do, but it has quite a lot of introductory material. I'm going to use it as footnotes on the way through. And PhysClips is the next one there, which, among other things, has an introduction to sound, including music. So, I was told it would be a very general audience, and so I should aim for something that won't leave the high school students behind. I thought the obvious thing to do is to go through the basics, to talk about vibration, how we quantify it, a little bit about waves, and then the particular wave of sound, and then to look at standing waves and resonances, because they're important in virtually all musical instruments. Then we'll introduce some of our research, for which we have to go a little bit more rapidly, some of the complications with string instruments, and in particular speciality of our lab is to look at the player-wind instrument interaction. And then what I intended to do was to finish a little bit early and leave some time for you to ask questions and perhaps push this talk in the direction that you'd like. On the right, there's a puzzle. And I've just put it there because quite often people react to music by saying, oh yes, I know about that, harmonics, and you can tell open and close. Yeah, the Physics 101 story is inevitably very superficial. And so there is the spectra of two different instruments playing the same note, and you're invited to say which of those is a flute and which of those is a clarinet. Just by way of a little teaser. So, if we look at a few musical instruments, and let's make some physicist sort of comments about them. They require energy input in, and for the string players that obviously comes from the arms, from the winds players for breath, voice, also breath. And the first thing that a physicist would say is they're remarkably inefficient. You see the players sweating at times, and they're putting watts or even hundreds of watts into the instrument and getting out milliwatts. They're typically 0.1 to 1% efficient. You might think that's terrible. It's actually about the same as a typical loudspeaker. About 1% is reasonable efficiency for a loudspeaker. And it's good that loudspeakers and musical instruments are only 1% efficient, because a watt of sound anywhere near your ear is enough to deafen, literally cause hearing damage. So you don't want watts and kilowatts coming out. It's just as well that a kilowatt guitar amplifier only puts out watts of power. Otherwise it might really be a kilowatt guitar amplifier. Anyway, so inefficient. And one of the reasons for the inefficiency is because we don't put in AC power, alternating power, we put in DC power. So the violinist's bow is moving in one direction, relatively slowly, and yet what we want is the string to vibrate backwards and forwards, and ultimately we want some air to be moved backwards and forwards and transmit a sound wave to our ears. So there are things that do that. It's called regeneration, and to convert from DC into AC, you need a system that's inherently non-linear. A linear system is something in which you double the input, you get double the output. I have to say this because in the 1990s, the literature people took over the word linear and non-linear, and linear in literary theory and criticism for a while meant boring and old-fashioned, and non-linear meant new. And so quantum mechanics, which is a highly linear theory, would be non-linear further. Anyway, it's for a physicist, linear means straight line. Yeah? So you need things that are definitely not straight lines to turn DC into AC. And that's some interesting physics, and we'll talk about that in a qualitative way. It's very important for music because it's actually this non-linearity that's responsible for the sounds of most musical instruments being harmonic. Percussion, it's another story, but for the sustained sound instruments, it's that very non-linearity that gives them harmonics and ultimately gives us the whole idea and phenomenon of harmony. In many musical instruments, there's a resonator that controls the pitch. There's a string for the string instruments. There's the air column for the wind instruments. And by the way, I put air columns there with the S in red because if you think about a typical woodwind instrument, it has this very interesting DC to AC converter, and we normally put a resonator on this end, but it also has a resonator upstream because it's coming out of a person's vocal tract, which a physicist's first order approximation is a pipe. So there's a pipe upstream and a pipe downstream for wind instruments. For the voice, there usually isn't, unless you have a high voice. Well, that's actually worth mentioning. The point about that is that many people say, well, the voice must be like a wind instrument. It's got these pipes there. But the point about that is that if I sing at 100 hertz, 100 hertz is a wave that's from the wall to here. And to support that, I need a pipe at least a quarter of the way long. And so it does indeed play at 100. But I don't have a pipe that long. I have inside here, I've got a pipe that's about that long, yeah? And you can hear the resonance of that, you can possibly hear that pitch. So this is the very piccolo soprano sort of pipe that I have that's got nothing to do with the pitch because your vocal tract and mine are probably only several percent different in length. And yet the pitch of our voices are
very different.
Thank you. Yeah. Oh, that one wasn't even rehearsed. Well done. So we have resonators that control the pitch, except in the voice, which is an interesting thing. When you learn to sing, you don't have the resonator to help you, and it does actually make singing difficult, which is why we start people off when they're only a month or two old. We want to give them plenty of practice at using this very complicated musical instrument that doesn't have a resonator to help them, except in some high voice cases. There's also a question of how we get the sound out into the air. And that's quite important because you've heard what happens to the electric guitar when you pull the plug out. The string itself, the string in a strings instrument, can pass through the air very easily without transmitting any energy from the string into the air. And so you've got the string, which is a small, dense thing, and the air, which is large and low density, and you want to get power from one to the other. Now, technically this is called impedance matching, but let's try to demonstrate it. Let me take this small, dense thing here and set it vibrating. I have the innards of a music box here, and maybe the camera can actually hear that because it's got a microphone. Anyway, I'll then attach it to something that's large and capable of pushing a substantial amount of air. And so suddenly we get some energy transmitted. So that's why the poor old bass player... That's why the poor old bass player is struggling to get through doors with this huge box, because we want a large piece of maple to push air backwards and forwards. Basically, that's the story there. For a wind instrument, it's easier because the wind player already sets air vibrating. And so it's already a sound wave inside the pipe. Some instruments have a trick for getting better matching between a narrow stream of air and getting it out into the large air. So those instruments have got this, which makes the instrument more efficient. Yeah? So you get this sort of slightly more woodwind sounding noise when you don't have the flare and different pitches and complications there as well. The voice has the vocal tract to do that, and it does do that, but as we saw with this little pipe here, it only does so for fairly high frequencies, usually much higher than the voice of the person that's using it. So it means that the voice doesn't radiate at low frequencies well, but does get rid of the high frequencies fairly well. And I just noticed that the behaviour of those bits are frequency dependent. The way in which these pieces of wood distribute energy into the air is very important in the quality of the instrument itself. The shape of the bells instrument is important in the timbre of instruments. And in the vocal tract, it's responsible for phonemes, the different speech sounds that we produce to a very large extent. So there's an interesting look at all the instruments. Some of these effects I'm going to go through next. But what I'd like to do just at the moment is say, have I got the level about right? Is there anything that I'm saying that's too puzzling? Is anyone lost and would like me to... I'm throwing in sort of interesting things so that my distinguished colleagues in the front don't actually go to sleep. But I do also want to make it comprehensible. Yeah? So, okay. That's all I really needed to say at that stage. So I spoke a little bit about how you set up these vibrations. How can we turn DC vibrations, DC power into AC vibrations? And a simple one to talk about is the clarinet and mouthpiece. So the clarinet has this little bit of cane about which the players are very precious, and it sometimes squeaks on you, which is probably why they're precious. Let me just wet it up. So why does it turn DC into AC? Well, let's imagine an experiment in which I measure the flow of air through this and simultaneously measure the pressure in my mouth. What am I going to get? Well, here's what I'm going to get, idealised in a simplified model. So I start off increasing the pressure, and initially I get more and more flow. The reason why this looks like a square root shape is because of Bernoulli's law and some turbulence downstream for anyone who's interested. But you can sort of imagine that as you increase the pressure, at least at first, the flow should increase. However, the more I push on this with the pressure in the mouth, the more it closes, until eventually, if I blow really hard, it just pushes the reed completely closed and there's no flow. So I think you can believe me that this effect of the pressure forcing the reed to close means that the flow must ultimately come back down to zero, and whether it's this curve or that curve is determined by how hard I bite. If I bite hard, then less pressure is required to shut it. Is that little qualitative argument reasonably clear? Because it's rather important to the story that I'm telling. So there is the pressure flow curve. And pressure and flow are analogous to voltage and current in electricity, in many cases to a very good analogy. We also talk about electrical impedance and acoustic impedance. And so if we look at this, we could say, here I've got the flow increasing with increasing pressure, and so in that case the resistance, the ratio of those to each other would be positive. So it means that I waste energy. I puff, some energy goes into the kinetic energy of the air, and there's some viscous drag, and one way or another the effort I put into expelling the air is wasted. It's like, you know, the electrical resistor that you put in the kettle to heat up your water. It takes electric current at high voltage and converts it into electric current at low voltage and does some work for you on the way, but you've lost work. Yeah? However, if we look at the right-hand side of this curve, we say that over here, the resistance is negative. If the resistance is positive over here, if this is something that destroys energy for you, this looks like something that would create energy for you. Negative resistance. Well, it isn't really negative. If I look at a point here, I would say if I drew a line there, it's still got positive flow and positive pressure. But for AC, for variation, it looks like the blue line. So there's an interesting story. DC would be a line going across here, or a line going across there. DC, it's positive resistance, it's taking energy away. But AC, the oscillations, the pressure going up and down, the flow going in and out, for AC, it's negative resistance. So I now have a mechanism that's capable of putting energy into vibrations. And of course, you know that must happen because these instruments actually work. And that, in a nutshell, is how it works. And of course, it's a system that's not a straight line, as I promised you, it's a non-linear effect. So we'll have a look at a couple of other ones on that. So, lip valves, reeds, and air jets. This is a lip valve. Will that movie run? No, I'll show you that. Well, that's actually Alex Tarnopolsky, a postdoc who worked in our lab, and one of the finest didgeridoo players to come out of the Ukraine. Didgeridoo. I'll show you a bit later on how those. Oh no, here's my slide. Here is a set of slides from that little movie showing the lips opening, and we've injected carbon dioxide here and taken Schlieren photography so that we can actually see the jet of air coming out through the lips, mixing with the CO2, changing the optical properties of the air and allowing us to see it. Okay, so you sort of know this story. If you seal your lips closed and then apply pressure behind, you can imagine the pressure building up. And eventually, the pressure gets big enough and they pop open. And once they pop open, warning, I'm cheating a bit here. Once they pop open, we'd expect that the pressure would reduce because the air has flowed out. That's the cheating bit. And then the elasticity in the lips pulls them back closed again, and then the whole cycle can repeat. Yeah? There's also another effect, and that is that high-speed air creates a little suction called the Bernoulli effect, and so that helps pull them closed as well. So there are two effects that could make lips vibrate and produce a vibrating sound even in the absence of a pipe to help them by providing a resonance. Okay, and here this is Jane, a flutist who worked as a research assistant in our lab, demonstrating how to play a flute. You blow across the top. And here are some lovely pictures by some French colleagues of ours, Benoit Fabre and his team, showing that an air jet is spontaneously unstable and it starts to wiggle. And if the air jet going into and out of, or going across first, the hole of the flute, if a pressure wave arrives in the head joint of the flute at just the right time, it can drag the jet in or push it out. And so if that arrives at the right phase, it's possible for the jet to be sucked in or pushed out and thereby add extra energy to the wave. Okay, so there's a, John Coltman, quite some time ago, wrote a lot about the sound generation in flutes. So there are the techniques of getting DC power into AC power. Let's talk a little bit about AC power, and I'll probably make this, looking at the age of the audience here, I can probably make this a bit faster than I might have needed. So first of all, oscillations. Physicists like to start with simple systems, and so we put a mass on a spring, and we get oscillation, and the frequency of the oscillation depends on the stiffness of the spring. A long spring is not very stiff, easy to pull out a few centimetres. A short spring is stiffer, and we'll see that with a stiff spring, the oscillation is a lot faster. And if we were to change the mass, so there is my mass spring oscillation with a small mass. Let me increase the mass. And now that's slower. 1, 2, 1, 2. So, let me get a small mass still. And small mass still, 1, 2. That's okay. Well, no surprise, I guess. Everyone was familiar with that. There is a little demo that I'd like to do related to that, because at the moment, you can't hear this. Well, the frequency of this is not a pitch. It's actually a tempo. In fact, it's molto largo, I guess. One. Anyway, so this tells us already something about our ears, that it's got to be going fast enough for us to hear it. Let's do that, and I'm going to take a very simple bit of apparatus that will be both mass and spring, and that's my ruler. So it's its own mass and its own spring, and you can see it wiggling there. And what I'll do now is show you that as I make it shorter, I both reduce the mass and make it stiffer, and it vibrates more rapidly, and eventually it does have a pitch. So we now know that when we make it shorter, the vibrations get faster, and so we've now proved in 2 steps that fast vibrations are high pitch. Yeah? Long is low frequency, short is faster, and then when we can actually hear it, long is low, short is high. So we've showed that the vibrations are what give us the pitch, and that the rapidity of the vibrations, the frequency, as we say, technically determines the pitch. Does that make sense?
Yeah.
No, I'm talking to the younger folks behind you. Saying, you now have the perfect excuse when you're sitting in class and going. Oh, no, it was actually the professor at the university who said you should do this, and it well, maybe you know. So, we know a little bit about vibrations. We need to know a little bit about waves. I'll start with waves in strings, because partly they're important to musical instruments, and also because I happen to have a string here, but finally because we can actually see the vibrations in this case. So I'll send a wave pulse along first. So what I'm going to do is hit the rope, and you can see a pulse go down that way and come back, and you can probably see an interesting thing happens at the reflection. I'm going to push it down, and when it comes back as a pulse down, comes back as a pulse upwards. So I'm getting a reflection, and the reflection comes up backwards. Okay, so that's an interesting thing. I'm now going to do to a wave, what happens when we vibrate something. And for that I want to slow everything down. We have this cute gadget over here. It's called a torsional wave machine. At least in our school of physics, that's what it's called. There's a hacksaw blade, a bandsaw blade along here, an elastic element, the springy element is down the middle, and these bars provide the masses, and the spring only very gently brings them back, so it gives me a very slow wave transmission. So there's my pulse, and at the moment it's fixed at the bottom, and you can see the wave get changed in sine before it comes back. Okay, I'll do something else at the moment. This is something I can't do with the string, and that is I can free up the ends. So I'm taking off the clamps on the very bottom one, and there's a bearing at the bottom. So now I'm going to send down a pulse and watch the reflection at a free end. So there it is, pulse to the left, big wiggle, and it comes back as a pulse to the left, yeah? So when it's reflected at a free end, it doesn't change sign, but when it's reflected at a fixed end, don't stand on that trombone, even if it's plastic. Okay, so when it's reflected at a fixed end, it's reflected with a phase change. It comes back on the other side. Now that has an interesting effect when we look at a travelling wave. So just imagine that we plotted the height of this as a function of time. And so we said, here is the height, and here is time, and it's got some original height, and I gave it a pull, and it started looking like that. It's just going smoothly up and down in what we call a cos wave or a sine wave, and that's very important in science because it's the simplest one for us to analyse, and therefore we pretend that they're everywhere. Yeah? How do you solve a problem in physics? You make it simple enough and then you solve it. And that often means make the equations linear and we get sine wave solutions. Sometimes it really works, but it's usually some approximations have been made. Even here, it's not a perfect sine wave. All right, so what I'm going to do is take a sine wave, which I'm going to generate with my arm. I loaded the synthetic one into my digital signal processor here, and I'll output it through. Anyway, I'll make a sine wave up here, and you'll see a sine wave travelling down. No surprise so far. What I want you to do is watch what happens when the sine wave is still coming down, but at the same time going up. Yeah, it won't happen for very long because there'll only be 5 or 6 pulses, but for a little time, 5 or 6 pulses travelling along here, some of them will be going up and some of them will be going down, and I want you to see what happens. So here's my sine wave going down, and now they're overlapping. Cool, eh? So what I want you to look for is this. While it's going downwards, I've got just this shape and it's going downwards. And then when it gets to the bottom and starts reflecting, there's at least a little while in which it's just doing this. There are some points, like the bottom one obviously, in which there is no motion. Oh, because it's got no motion, we're going to give it a special name and call it no. So that's the bits where there are no motion. And the opposite of those, just to be original, we'll call antinodes. Dividing the house, the antinodes will pass to the left, the nodes will pass to the right. So there's the nodes and the anti. Well, just see if that's what you see in this during the few seconds that you have. Now, while they're starting to, can you see that there's a point about here and here and here where it's actually stationary. Now that is a wave that's going nowhere, so physicists with their typical ingenuity call that a standing wave. So that's a standing wave, which happens when a wave meets its own reflection going back the other way. And part of the reason for that is we had reflection. Well, of course, we have reflection at this end, reflection at that end. When we look at a string instrument, we can get reflection at two ends. In fact, if we take one of these instruments, we see that the string is going to be stationary here and stationary here. It's fixed at both ends. This is what's known in physics as a first order approximation, and which is known to my mother as a lie. It's obviously a lie because of this demo that we've just already looked at. Yeah. The whole point of this belly is that it can move, and the reason it can move is that the bridge isn't stationary. The string gives some of its vibration to the bridge, which gives some of its vibration to the belly. So it's not exactly stationary unless it's a concrete electric guitar or something, and that's the whole point. So what I'm going to do then is fix the wave at both ends, and just put in a little bit of energy. So fix at both ends, and you can see it can wave like that. And if you were to imagine that on one of my graphs, if I said, okay, here it is, it's fixed at that end, and it's fixed at that end, one of the possible sine waves I can put looks like this. I'm drawing in another half of it to show you that there is one whole cycle. I call that a wavelength, and I'm sorry if this upsets anyone, but I just cannot bring myself not to use a Greek letter. All right, so there it is, and the length of the string is L, so I'm going to say that the wavelength is twice the length of the string. But that's not the only possible wave that I can see there. It would also be possible for me to have a wave in which there were one whole cycle in there. So let me see if I can do that. So they're 1, 2, if I go 1, 2, 1, 2, can you now see a node in the middle and vibrations on the side? Vertically it's much more difficult. I can build, oh, that's too fast. With this particular string, it's very good for me, I get a good perspective on this. There's something like that. Let me show you, I'll get my assistant here. I'll get my assistant. So let's escape out of that. Let's go to physics animations, and we obviously want the, look at this character, anyway, he's obviously a crazy man. Standing waves is what I'm interested in here. So let's make that a little bit bigger. And so we'll go through this. So here I'm going to want waves on a string. So there's my story about the string that's fixed at one end. Any wave will do that standing wave business. Here's my animation of the different waves that are possible there. But let's go and see this actually being done. The same rope, I hung a weight off the end to get constant tension.
Frequency gives the second mode, and so on. If we increase the frequency enough, we'll be able to hear the vibrations. Let's do that next.
Okay, so he's got a terrible voice, that bloke, but my students assure me that he has the wonderful advantage that he's there at 2 a.m. on the morning of the exam and prepared to go through it all over again. Anyway, so that's the story I was starting to draw for you there, that the waves have gone to twice the length, to once the length, to 2/3 of the length, to half the length. And you could see them there, and maybe you could see it in my rope demonstration. I'll leave that for people to play with after, because as I say, the horizontal ones are much easier to do and to see from the end. So, let's have a listen. So I'll take a string that's big enough to play. Now part of the reason for bringing this is that you can actually see the vibration here. And you can see that it's stationary there, almost stationary here, thanks Mom, and large amplitude in the middle. And you might say, if I were to just gently touch it right in the middle, I suddenly get a wave that's only half the length. So I'm not stopping it, I'm not doing that, I'm just touching it very lightly. And it keeps vibrating in that way. Yeah? So I can produce that, and I can also get, oh, and that's 3 times the frequency. So wave twice as long as the string, I call that my base or fundamental frequency, and then twice that frequency. Now the wave is that pattern with a node in the middle, a node a third of the way along, and I can get the rest of those. In case you don't happen to have a base about you for doing this at home, the School of Physics manages to have a few, actually. It's a surprising feature. These are more easy to come by. And I'm also going to take the liberty of tuning this down to about a C. So I've now got a C string on this guitar, and we'll take note of the pitch as we go. So and the exciting bit when the teacher drew parallel lines on the blackboard. Okay. That's what the parallel lines were for. Okay, so I've tuned that note down there, so this is now my fundamental frequency, which I'm going to call F, even though it's a C, F the frequency there. And then, when I halve the wavelength and double the frequency, I go up a full octave. So, and call that an octave because if you, like Western scales, 1, 2, 3, 4, 5, 6, 7, 8, 8 for octave, octave for 8 or something like that, and then, so what I'm doing now is getting all the rest, so that is 2F there on my graph, 2F, and then we're going to want 3F, 4F, 5, 6F, 7, 8, 9F, and 10F. I'm going to be off the edge. All right, we've already heard those. There's 2 Cs. And then these mics should be live. So I'll write down what I heard there, and you tell me if you hear it too. Is the top one still audible? Up the back even? Good. So where are my engineering friends making noise up in the back row of the lecture? Okay, so what I heard was a G, and then a C, so that's 4 up there, and then an E, and a G, and then a note that I'm going to call, it doesn't actually fall on our scale. So I heard it as something like that, A half sharp. It's roughly what I hear it, and then after this, some notes up there. And this is called the harmonic series. A harmonic series, and all I've done with the frequency there is increase it by the same amount each time. So it's 1, 2, 2, 3, and then etc. There's that one that's out of tune, and then there's the next octave and going up. And then there's another one that's out of tune, and you need a bit of practice to play those higher ones. So this tells us something quite interesting. It tells us a few things. One of the things it tells us is that our sense of pitch is not simply related to the frequency, because I add the same amount of frequency on each time, I don't change the pitch by the same amount. I've got to double the frequency to get an octave. Here is an octave, there is another octave, there is another octave. And in fact, if you look at this, you'd say, ah, of course, it's a log curve. The musicians actually use logarithmic semi-log graph plating. So the musicians, when they put the axes on their music, which doesn't happen all that often, yes, this is the log of the frequency, and this is time here, and it all makes sense. Ah, phew, why didn't they do that? And us scientists would be able to read music. Okay, so it tells us about the logarithmic sense of pitch that we have. What about standing waves in air? Well, why would a wave reflect at the far end of a pipe? This is a question that, it is one of the FAQs on our Music Acoustics FAQ on the page that I showed you. If you imagine a lump of air travelling along here, when it gets to the end, it's got momentum. And once it gets liberated outside, it can not only keep travelling, but it can spread out. And this spreading out, combined with its momentum, means it actually sucks out some air behind it. So behind the pulse of positive air that comes out here, there's a little bit of suction, and that sucks the next bit of air, which sucks the next bit, and so a suction pulse goes back the other way. So it's possible to set up reflections in a pipe. Let me show you those, because it's worthwhile seeing an animation of that waves.
Pipes have resonances that we can excite indifferently.
Okay, so, oh yeah, let's talk about that.
Spheric. So the sound pressure is approximately 0. So the pressure wave is reflected with a phase change of pi.
All right, so he's a bit technical, but that animation, I think, shows you the effect of the pulse gets reflected with the same sign at the closed end, and then here it comes to the, here it comes to the end, and its momentum plus the spreading out causes a
Sound
suction.
pressure is approximately 0.
I'll let you run that in the privacy of your own home if you want to be convinced. But the point is, at the either end of a pipe, we get reflections. So, let's take this pipe, and we've already seen how flute players make them vibrate, and they actually leave this open to the air. They don't seal it off, they blow over the top. It's a bit like blowing across the top of a bottle, only they blow across. And I'm going to close all the little buttons here. So I've got a physicist's flute, you know, it's just a cylindrical pipe. And so it's now open at this end and open at that end. And so it'll play that note there. And if I were to draw a diagram of that, I could now say, well, if this were a graph of pressure, and I was measuring pressure with respect to the atmosphere, then this applies to the flute. The flute is connected to the atmosphere at either end, so at either end of the flute the pressure is roughly atmospheric, but it can be anything it likes inside the pipe. So one of the notes that the flute could make would have a pressure wave like that. If I looked at its velocity, I'd say, well, actually the velocity could be quite large at either end, and it might look like that. But I won't talk about the velocity wave, I'll just talk about the pressure wave in the flute. And it could have a wave that's twice as long as the flute, which is that one, which is now 1 octave higher than my guitar note. So my flute is starting off on middle C, and we'll get it to play the other notes by playing by blowing faster and faster. And if you tell me when my eyes pop out, I'll know when to stop. Yeah? So there's the lowest note. Middle C. There. And there's the one that's out of tune. So I missed one on that. Let's see if I can do that now. And then they're out of tune, and they keep going up. So it was the same series, but an octave higher than on my guitar. The guitars, by the way, are transposing instruments, and the guitar music is written at the pitch I'm writing now, but it sounds an octave lower than the way it's written. So I want E, G up there, and then I want one of these half sharp things again, and high. Well, I didn't actually get any higher than that because, as I say, my eyes pop out, and it probably isn't covered in our OHS. So there's an interesting point. But what about if I were to get an instrument in which this were closed at one end? If it were closed at one end and open at the other, so if I had a pipe that was like this, let me rub that out and move it a little bit to the left, because I'm going to need lots of room here. Suppose I had a pipe like that. I could actually have a pressure wave that's 0 here, maximum here, and it could be a full 4 times longer than the pipe. So my first one, lambda, would be 4 times longer than the pipe. So let's just remember. So there's the low note on the flute. Middle C, keep that note in your head. It sounds high when I sing it because it's towards the top of my range, but there's a middle C, which is, whoa, let's go stretched again, contracted. Let me now turn this into a clarinet. Overhead transparencies have a big advantage over PowerPoint in that you can use them to convert a flute into, ta-da, the clarinet. Let's see. So it plays approximately that note, but to play that note, I only need about half the pipe, and it will actually go. Goes down to C below middle C, plays a note an octave lower than the flute, which is why the flute sit up the back next to the bassoon, a classier place in the orchestra than the showy front row with the over. So there's the clarinet, and I'm going to ask you, what does it sound more like? So sort of asking you, what's more important, the end effect on the or the pipe? Because I've got a flute pipe and a clarinet reed. Don't fool us, we'll put. Anyway, so which do you reckon? Who's voting for flute? Who's voting for clarinet? Who's voting for saxophone? Yeah. The reason for that is there's a saxophonist upstream from the reed. That's why. Which is an important part of research. I could talk a lot more about sound and the things that are related, music, things that are related to it, and consonance and harmony. And you can see that there's quite a recipe here. But what I'd like to do now is to put aside the sort of teaching bit that I've been doing at the moment, and instead go back and look at some of the work from our lab. So, music, acoustics. These are, roughly speaking, our research areas in the voice, the ear, and music, and various other things. There's FAQ that you might be interested in. If you are using portable entertainment devices, you might want to check your hearing weekly to see how it's going. We have a facility for that. But I'll talk first about the bowed string instruments. And we have done a little bit on this. I know a dozen papers, I suppose. One of the reasons it's not our major effort is that the violin's been around for a while, and some very good physicists have studied it. So there weren't that many really good problems left for us. Some applied ones that we've done, but let's have a look at, for a start, let's have a look at how the bow excites the string on the violin. And the wife of one of my colleagues, Heidi Harris, John Smith's wife, made this nice little animation showing how the bow works with the string. the bow sticks onto the string, static friction we would say, it moves the string along, and then when the kink arrives at the bow, when the kink, suddenly the tension is pulling in the same direction. While the straight bit is on, the tension in the string on one side pulls it down, the other side pulls it up. But when the kink gets there, they're both pulling down, and suddenly it exceeds the friction limit. It's like you get to a point where you fall over and slide, so you exceed the critical friction value, and then all of a sudden the string travels very rapidly and picks up the link on the other side. So that's what's happening there. It's called Helmholtz motion, which tells you how old the problem is, yeah? So it was solved in the 19th century with sophisticated and subtle techniques at the time. So let me tell you that even though that problem had been studied for 150 years, there was still an interesting puzzle left for our research lab, and it was this. The story that I just told you imagines that the string is infinitely thin, but it isn't. The string is bowed at the surface of the string, so as well as pushing it sideways, you twist it. And when you twist it and release it, it not only does this, but it does this, it wiggles. And it wiggles at several times the frequency of the transverse motion. But not exactly 6 or exactly 7 times, but sort of 7.3 on one string, 7.9 on another. It depends on how you tune them, in fact. Now that was a puzzle because you'd think if I've got non-harmonic oscillations in the rotation and add them to the harmonic vibrations of the string, I'm going to get vibrations that are not harmonic, vibrations that don't repeat themselves. And we know what they sound like. They sound awful. As soon as you get more than a couple of % of variation in the frequency from cycle to cycle, it sounds dreadful. So why doesn't the violin sound dreadful? Well, it does if you give it to me, but why doesn't it sound, well, when Daniel plays it doesn't sound dreadful. And the reason for that, people said, was this twisting motion must be small. It must be within that sort of % or so that it doesn't offend our ears. But we thought, well, let's look at it. We measured that and we found the size was as much as 30%. New explanation required. Well, the explanation is actually simple. What happens is that the interaction between these two is strongly nonlinear, must be to convert DC power into AC. That means that we can couple oscillations and we can get what's called by physicists mode locking. We can force the vibration, the rotational oscillation to happen at exactly 7 or exactly 6 times the transverse frequency. So there was one that we did on violins, and some less fundamental but perhaps more interesting problems on other problems on violins and the other members of its class. You can read that if you like on our site if you wanted to go into the details of it. I'm running out of time, and I just wanted to do a couple more things with you. I realised that I didn't show you, I only ever showed you my air flute. So this, that's not an air flute. This is an air flute because the thing that does the vibration in this is air. Now, I mean, there's some silver to hold it in place, but the important bit of this flute is air. I'm now going to play my aluminium flute. Here is my aluminium flute in which the material that does the vibrating is now aluminium. So I want you to look at this and say, I'm going to send a sound wave along this, bounce off the far end and come back. It's solid. There's no air contaminated. It's a pure aluminium flute, this. And what I want you to tell me, is this a bass aluminium flute or a soprano? Don't say anything. Now, the way you play this, since I'm not an aluminium breathing species, I can't blow in the end and excite it. And so I excite it by rubbing it with weightlifter's rosin. Now, you might think this is pretty silly, and it is, except that a related version, a sort of handcrafted version, is called a stroke rod, and it's a real musical instrument, and the Sydney Symphony has a set. They're called for by Richard Strauss. And it's our mate Colin Piper, the percussionist from the Sydney Symphony, who has the honour of playing this when it's required. He says, it's one of the most embarrassing things to play. There you are, up the back, with your gardener's glove on, dipped in the weightlifter's rosin. holding this great big bar up in the air, and when 8 gives you the signal, a noise had better come out or you're going to look an awful dill. So I'm doing that to let you know that the sound might not come out. So I've got nothing rosin on that, maybe there's still enough, and maybe not. Yeah, you can hear a little bit of that. There we go. Sorry, Ed, I'll get the next one. I'll get it on the second time. Bye. Ah, there we go. So in fact, it's a soprano instrument. Aluminium is much denser than air, so that would make you think, the wave's going to go slow, but it's a lot stiffer. It's much easier to compress air than aluminium. Anyway, so that was fun. I thought I'd just show you another couple of flutes that we have here. So we've got a couple of flutes down here on the floor, and they're a bit big for me to blow. So I'm going to put energy into those in another inefficient way. They have a metal gauze across here that I can heat up on the Bunsen. And once I heat it up and take it away from here, it's going to heat the nearby air, which will then rise. So I'll get an airflow through the gauze, which will set up turbulence, and any pulses that come back can enhance that and set up a standing wave for me. Yeah? So once that's hot enough, I can get that to play. So it's an interesting musical instrument. Its articulation's a bit slow. There, just because it's fun. And not any advantageous educational experience. I'm probably giving you, that's not the most attractive camera angle there, Shane, I'm sorry about that. It's actually launched this way. Not hot enough.
Yeah.
So,
It will take longer.
here we go. So, to get my convection to start a wave in this rather larger body, I'll need to get it fairly hot.
You see the convection wave with this
Oh yeah, you can see that. Isn't that cute? Coming out the top, the turbulence being set up as it convects through that gauze.
Yeah.
I can hear it there, but perhaps you can't. So, yeah. Give it just another 10 seconds. At this stage, you would normally tell jokes about unfortunate sections of the orchestra, but one has to be a little bit careful with this particular audience, just what we would say. There's that one about how can you tell the difference between a drummer and a drum machine. With the drum machine, you only have to punch the information in once. And the drummers would now say, oh yes, at least I can get the flute here to play and you can't. I'll just finish by talking a little bit about some of the research going on in our lab. We're very interested in the interaction between the player and the instrument, because after all, that's what's really interesting. I'll put this down and maybe leave it for later. That was a waste of time, sorry about that. What can I tell you about that? Here's, if I go to my PowerPoint, okay, let me just show you this slide. So this is a project that we wanted, and this is there, isn't it? Okay, Andre Almeida, David George, worked on this. What we wanted to look at was how do players actually manage to do it? They've got various input parameters and a range of output parameters. How can they manage to play in tune? Here we've got the pressure with which you blow. Here the force you apply with your lips, which are the two main things controlling the pitch, though there are others. And the black lines are the frequency, and the shadings are the sound level. You could say it's approximately loudness. So loud here, soft up there, sharp here, flat there. If you're a clarinetist and they ask you to play a crescendo, they want you to go from the light grey area to the dark grey area, but they want you to do it at constant pitch, so you stay in tune. They want you to follow one of these lines. So you have to compensate the pressure that you play with the lip force that you apply. And so that's an interesting little project that we had, and I'll put that away for the moment because I want to tell you how we did that. So music acoustics, it looks like a clarinet project, and we had a very helpful assistance in that. Here's a little concert, in fact, showing two of our assistants. This is Deborah de Graaf, a very well-known clarinet soloist around town, and here alongside is our assistant. So the trick there is for you to tell which is the robot playing the instrument and which is the human, and at what points do the two parts cross over. When is the robot playing the high line and when's the human playing? And why do we have a robot playing clarinet in the lab? For that experiment that I was just talking about, we have that because a robot, you can say, all right, I'm going home now, can you please investigate all possible combinations of pressure and force between these values, and I'll meet you back here at 6 in the morning. Yeah? Most of our human subjects not only don't want to do that, but probably can't. They're so used to exactly compensating all these things, you can't investigate how all the different controls affect the sound. Well, it's fairly rare for us to make robots to play instruments and look at them that way. And we're not trying to put musicians out of a job, it's rather that we're really interested in finding out how the instruments work. So we've been doing experiments where we put devices inside the mouths of wind players and we send in hundreds of different frequencies and measure what comes back, so we see what's going on inside their vocal tract while they're playing. Lots of other interesting things, but if you are keen, our website's there to talk about our research. Every one of our projects has a simple introduction as well as the technical papers. And so I think I'll stop there and say, for those of you who want it, there's plenty of homework.
Thank you very much, Joe. I bet there are some questions now. There's time for it, probably.
I just wanted to ask about, in terms of the voice of the vocal cords, you talk about things being fixed at both ends. The vocal cords are sort of fixed. I wondered if you could discuss, and I'm particularly interested in things like harmonic singing, harmonic chant, where you can actually get so-called sub-harmonics and other harmonics, which obviously requires playing around with the architecture of your vocal cavity as well. So I just really could discuss both the fixing of the vocal cords and what effect you can get and do harmonics.
Yes, I think if none of you have anything to do between about now and 9 or 10:30, we're fine. No, roughly speaking, the story that I told you for the trombone player or the didgeridoo player also applies to your vocal folds. They're not cords, they're folds of flesh that when you close your glottis can close off the airflow, and when you squeeze a bit of air out, they'll pop open, and under certain conditions, that will lower the pressure again and allow them to contract and close, again with the help of the suction generated by the flow between them, and that can repeat, which is what's going on there. However, because the vocal folds actually bang into each other, it's a very non-linear process, and that has the result that it has lots of harmonics, lots of frequencies that are exact multiples of the vibrating frequency are generated. And normally, those go through your vocal tract, and we use the vocal tract to shape the spectrum, so you can tell the difference between R and or, and tell what words I'm saying. What the harmonic singers do is to select just one of those frequencies and then adjust the mouth shape so that it has a resonance at exactly one of those. So remember that it's very short, likely to pick up one of the pipes. This, by the way, works much better for men than for women because you're starting low. And so you pick up just one of the high harmonics, you boost its radiation so it's loud outside, and if you make it loud enough, it doesn't have to be very powerful because the ear is much more sensitive at high frequencies than low. If you make it powerful enough, you'll hear it as a separate note rather than just a component of the fundamental note, which is what happens when I sing. Unfortunately, at this stage I have to admit that I can't do it, and the postdoc in our lab who's very good at doing it is on his way back from the International Conference on Acoustics at the moment, so we can't give you a... There are demos on our website. There's a page on it. If you look under voice, there's a page on harmonic singing with Jermaine giving examples of harmonic singing. Oh, can you give a demo? I should have asked.
But I just wanted to also ask you, what's the easiest harmonics to get? The so-called subharmonics or any particular harmonics on the way up? Are there any kind of...
How would you get an octave lower than this? Well, the way you do that is if you've got vibrations like this and you do something to them so that every second one is different. So if you went bang, bang, now the frequency is half that frequency. So all you actually have to do is boost every second vibration in some way and you get half that frequency. There are other ways of doing it as well, called heterodyning. If you can produce a frequency and one that's 5 notes above it, the interference between those two will produce a sound that isn't there in the air but is there in your ear. But there's some subtleties in there. It's a very interesting story, as you probably know if you've studied it. And as I said, we have a web page on it, but I don't want to get too far into that because I'm sure people want to get home and they possibly have their own questions. Yep.
Go ahead. Oh, this one's perhaps a bit simpler than the last one, but perhaps you've gone over it and still a bit puzzled.
Yeah.
When you've got a short pipe, a longer pipe, and you're plumbing that with your lips, you're sort of producing the same frequency, but the pitch gets deeper and it seems to get louder in bottom. So what's actually happening to the sound projects is you go from our lips to small.
Okay, so my lips are vibrating much more slowly here, and I hear that as a lower pitch than this.
The actual sound wave of your lips is a different frequency.
Yeah, this is actually helping produce the vibration of my lips. I can make the lips vibrate without that help, but it's much easier to have that help because when a pulse of low pressure comes here, it sucks my lips open and then can get a boost from the pulse going back the other way. So that's why it's easier for me to do that at that particular pitch. I can do it a little bit off the resonance of the pipe, but not so easily. Yeah? And if I have a shorter pipe, the reflections come back much earlier, and so the pitch is higher. And that's true whether I won't be able to blow across that one, but it would be true for that as well.
You had a question.
Yes.
My question is in relation to voice too. The two major formats, the first and the second, I always think the first one is parental and the second one is the mouth tongue. What causes formats above that? Like I use a particular vowel, an air vowel, and I lay flat. I have formats that go up to the 21st harmonic. Now, especially one on the 8th that matches the 3rd. I really can't begin to explain why those higher harmonics are so obvious.
Okay. Well, see which bits of this I'm going to use. Your story is actually quite complicated. What do I mean by a formant? So this pipe resonates, and imagine this is my vocal tract, almost closed by my vocal folds. It likes that frequency and that frequency, and if I could blow faster, there's a series up there. So there are lots of resonances of this pipe. So here it is. There was the first one, looking like that, and then the next one above that, let me continue this down here, the next one looks like that, and it's 3 times that frequency, and the next one looks like, hang on, let me see if I can get this right. 1, 2, 3, 4, 5, yes, that should be about right. So I want that. So I get all the odd numbers. I get F, 3F, 5F, 7F, and my vocal tract, if I use the vowel it's almost exactly that. My vocal tract, this comes out at 500, 1500. So there are the frequencies that my vocal tract likes to help. But my voice doesn't do that. So let me draw a spectrum with my voice. So here's going to be the voltage I get on the microphone, let's say, as a function of frequency. And here I'm singing at 100 hertz, and my vocal folds are doing this, and there's lots and lots and lots and lots and lots of those. And then it gets to my vocal tract, and the vocal tract likes to help the 5th harmonic. And it also likes to help the 15th harmonic and the 25th and the 35th and so forth. And so what comes out of my mouth is still the same frequency, but some of the high harmonics of it are boosted. And whether it's this one or that one depends on whether I'm saying ah, ooh, ooh. So that's what the formants are. These are called the formants, these bands of efficiently radiated sound out into the air. Yeah? Now everyone has them, just like every pipe has them. Some people can get more gain out of them. Some people have stronger gain in the vocal tract than others. And singers work on that. In particular, male singers work on a trick to compete with women. Women have the big advantage that their natural singing frequencies are in the range where the ear is sensitive. So they can be very loud with relatively little power. So male singers have to think, how am I going to beat that? And they have a trick of lowering the larynx, which helps get more energy from the vocal folds into the main part of the tract. So that usually happens up here, somewhere around about 35th harmonic of that note or whatever. Around about 3 kilohertz or so.
So it's still a function of the basic tuning of the first and second form, that they're related to the particular...
they're all related to the geometry, and the way you change them, as you said, you open the mouth to change this one, and you move the tongue to change that one, but either change affects all of them, though to lesser degrees. And then the very high ones depend on fine detail of the anatomy. When the wavelength of the sound gets small, they interact with even the small scale perturbations in the throat.
What about the singer's formant they talk about that actually begins down in the folds rather than the resonators? Okay, so if you said, here are my vocal folds going into a pipe that is open at my mouth and almost closed here, what you could do if you're an opera singer who doesn't have the benefit of a microphone is you could lower the larynx and essentially do this. Now we have a little pipe connecting to a big pipe, and this works a little bit like a bell. A small area into a big area, it matches the very small area here to the medium area here, which then matches to the outside world. So it's very efficient
at getting sound power from the larynx out into the main vocal tract, and so you get a little boost. And it happens up here at around about 3 kilohertz.
So that's not for formant 1 or formant 2, that's particular other formant, the singer's formant.
The jury is still a little bit out on that. According to one very distinguished scientist of the voice, it's a fusion of the 4th and 5th formants. According to others, it might not be that. It might just be this impedance matching effect on its own.
Mm-hmm.
So it's difficult to do studies on the voice for practical and ethical reasons. You can't do the experiments that physicists would normally do. Let's put a transducer in here and fix that and adjust this. Yeah? So we do quite a lot of work on research. We have to be very cautious because it's very indirect. Yes?
What do you call that interval between the 5th, the 15th,
The 5th would be, in my case, so 25 to 15 cancel the 5s, 5 thirds.
But you mentioned that the gap, the resonance of the human voice.
Yeah. This is only true for one vowel. It's only true for the vowel where my voice most closely approximates a cylindrical tube, and for me that's the vowel If I go like that.
So it doesn't happen in all voices?
No, or all vowels. It only happens for that one specific.
So that it happens for the vowel in your voice, but it's not in other voices?
It's much the same for most people. It's just that in mine it comes out almost exactly like a cylinder.
So I'm interested in the mathematics of it, the enumeration.
Yeah.
There's
there's no integers in it. They're all real numbers, and they vary hugely from one person to another and from day to day. A little bit of inflammation in the voice, or you pull that tooth out, and you could shift the high frequency. It's quite a lot. So the harmonics are more or less exact because of this regular nonlinear vibration. But which ones of them get boosted by this pipe? That's almost entirely a linear effect, and so it's just a multiplicative factor in the end. Vince?
Going back to the violin, you
Yeah.
mentioned the transverse waves and the torsional waves. Isn't the reason that the torsional wave doesn't get through because of the bridge? The bridge couples the transverse wave much better.
Yeah. The torsional wave, I should have said, is very inefficient because it can't twist the instrument, and so it doesn't radiate itself. No, that's not the worry. The worry is that it's inharmonically related to the transverse one. Like one cycle of the string might happen when the string is twisted that way, and the next one might arrive when the string is twisted this way, so that successive translational cycles have different periods, or the frequency changes.
It affects the tension.
It affects the point at which the string breaks free of the bow and starts another cycle. And it does. It produces what we call jitter, non-periodicity in the string. And a little bit of that is good. It makes the sound interesting and not synthetic. But more than a couple of percent sounds dreadful. And so it's therefore clear that it isn't more of a couple of percent jitter, even though there's as much as 30% ratio of the surface speed to the overall speed of the string. Richard, I think we should let people go and ask those who are keen to stay, because I can stay, but I'm worried that we're out past people's bedtimes. Oh, see if there's any leftover instruments there.
Oh, well, I never. Gift for you, Joe. Encourage you to play a bit more of that modern jazz this evening.
Oh, thank you very much.
Thank you. Excellent. Those physicists that need to be in bed before the 9 o'clock news, please feel free to leave now. And, other people may want to stay. Obviously, it's a very engaging topic. There'll be more questions, I'm sure. So thanks again, Joe.
My pleasure.